partner is Kumar. Together we're gonna proceed to explain about our project and its endeavors. Okay, let me go through an overview about our project. So we are designing and developing a transistor level design for the smart tank level monitoring system, which enhances water management in smart cities by enabling real-time monitoring and efficient control of water storage, reducing waste and ensuring sustainable supply to the housing areas and houses.
Then, the objective of our project is to develop a layout for the design circuit using industry-centered CMOS design rule and validate the layout with DRC rule check and layouts versus schematic, which is called LVS, to ensure manufacturability. Then, design a transistor level schematic for smart tank monitoring system sensor interface.
So we are designing projects with respect to the United Nations Sustainable Development Goals and Target. So there's 3 SDG that's related to our project, which is the SDG 6 clean water sanitation. The relevance is that our design system optimizes water storage and distribution, reducing waste and improving efficiency in urban and rural water management. And the next SDG is the SDG 9, which is the industrial innovation infrastructure. So the relevance is that smart water monitoring in our project enhances urban infrastructure resilience, ensuring sustainable water supply in smart cities. The last SDG is the SDG 11, which is sustainable cities and communities. The relevance is that the real-time tank level data enables cities to manage water resources sustainably, preventing shortages and promoting equitable access.
After that, our methodology for our project is to specify what are the inputs and outputs we're going to use in this project, and then derive a Boolean equation for our project, and then we draft our schematic in layout. After that, we create the test bench and generate a waveform for the schematic. After that, we create a schematic and layout in Mentor Graphics software and evaluate the design using DRC rule check and also layout as a schematic. This is our input output for this project. We have 5 inputs and also 1 output. The 5 input is first one is top level sensor. B, it's represent as A, and then B is bottom level sensor, and C is pipe leak detector, and then D is float valve feedback sensor, and also pump status sensor. These are the inputs, and also we have one output, which is to pump is turned on to fill the water tank. After that, our Boolean equation is derived as shown in the slide above.
So this is the truth table of our design. So particular to the inputs and then the output that we set, which is the water level need to be on. So the output should be 1. So far we have 5 inputs. So the total combinations that we could get as an input is 32 in total, and then we are focusing on A, B, C, is 0, and then DE is 1. So the output should be 1. So the only combination that is relevant to our to this input and output that we set is the 00011. So based on the Boolean expression and then the truth table, we first we drafted the schematic, the layout, and then the stick diagram and the layout for evaluation, and then we evaluate that it is evaluated by the lecturer, and then we gone through a lot of drafts, and then finally decided the final draft for according to draft for the schematic, and then we drew a stick diagram to design our layout later. So we went through a lot of evaluation, and then we rectify a lot of things. So this is the final draft that we had before we proceed to designing the schematic and the layout in Mentor Graphics.
After that, this is our schematic design for this project, which we have designed in this software, and we also got no errors in the schematic. After that, this schematic also consists of two inverters, which is on the left, and the top and bottom one. After that, the series connection is represented as the PMOS, and then the below part, the parallel connection is indicated as the NMOS. Then, from the schematic, we have generated a symbol which we will use in this test bench. For this test bench, we create another schematic sheet to design this test bench. The test bench is actually to verify and validate the schematic circuit, whether it is in correct connection and design as our expected result, which is similar to the truth table. In this test bench, we connected the pulse signals to each inputs, and also we connected a DC supply in this case schematic. After that, we generate the waveform, but we have a complication in this waveform actually, because the output is not as what we expected. Even though the test bench schematic is successful and without no errors, but it seems there is some output errors while we generate the waveform. So the possible reasons might be the probe declaration for the each input and output. As we can see, the input seems correct pulse wave, but there is a noise around it, and also obviously the output looks not good, because the probe might be faulty.
Okay, this is the layout design that we started to do in our Mentor Graphics right after schematics. So initially we tried to attempt SDL, schematic driven layout, which is a type of technique it is used in Mentor Graphics to straight away produce the layout from the schematic. But the attempt was unsuccessful because as you can see in the picture in your left, it is haywire, or it's all messy. The connections, everything is messy. So we decided to do the layout from the scratch, and then the picture in your right is the layout that we did from the scratch. After we design the layout, we attempt DRC, which is the design rule check, in the system itself. But initially we found that there's 5 errors, and then we adjust everything, saw the measurement, we refer to the measurement and everything, and then it was reduced to 3 errors, but still we had errors. After that, we checked the grid, and then we precisely measured using the ruler and everything. Finally, we produced no errors for the layout.
After that, we evaluate our layout through LBS, which is layer based schematic. Initially, we got hundreds of errors from the LBS. This is because we didn't declare the inputs port for each at the poly. So we resolved those issues, and also we successfully reduced some errors up to 39 errors only. But unfortunately, we couldn't resolve those 39 errors. Those errors are actually mainly on the LVS. When we violated LVS, it couldn't identify the nets and also ports as well. So we tried our best to resolve this issue, but unfortunately, we cannot resolve this 39 errors. For this is our final output from our project.